Okay, let's finish this. We were on the displacement versus time graph. We were on number 9 that says, did the object ever return to its starting point? Well, if you understand what the graph is showing us, that question's pretty straightforward. So the graph is showing us that the object moves 6 meters east in 3 seconds. It then stops, and then it moves 6 meters west. And at 8-second point, it's back at its starting point. But it doesn't stay there. It then keeps moving, and it goes another 8 meters further west, and it stops. And then it goes back 8 meters. So here at 15 seconds, it's also at its starting point. But it doesn't stay there. It keeps moving, and it goes another, 8 meters east. And it stops. And then it turns around, and it goes 8 meters west back to its starting point. So yes, it returned to its starting point at 8 seconds, at 15 seconds, and at 26 seconds. Okay? What was the average speed in the first, I think that's 8 seconds. Notice the difference in what they're asking here. Up here it was, what was the speed at 2 seconds, the speed at 6 seconds, or the velocity at 6, at 2, at 13. But here it's asking the average speed and the average velocity in the first 8 seconds, so over a period of time. And so we have to go back to the fact that average speed is equal to distance over time. So what distance did it travel in the first 8 seconds? And then average velocity with the arrowhead is equal to displacement over time. What was its displacement in the first, in this case, 8 seconds? So we go up here, and look, we already found the total distance in the first 8 seconds. It went 6 meters east, it stopped, it went 6 meters west. Its total distance was 12 meters. So here it would be 12 meters over 8 seconds. That's like 3 over 2, so 1.5 meters per second is its average speed. What is its displacement in the first 8 seconds? It's 0. It's back to where it started. It went 6 east and 6 west, so it's 0 meters over 8 seconds, and so its average velocity is 0. Okay, so notice the difference. What is the velocity at a particular time? You find the slope. What is the average speed or average velocity over a period of time? You do VAV, and you find the distance and displacement and divide it by that time. All right, number 12. What is the total distance traveled by the object? So you have to add all the pieces up. So 6 plus 6 is 12, plus 8 is 20, plus another 8 is 28, plus another 8 is 36, plus another 8 should be 44. So the total distance traveled should be 44 meters. What is the total displacement? Either you can do, it went 6 east and 6 west, 0, 8 west, 8 east, 0, 8 east, 8 west, 0, or you can just realize, wait, it finished on the line where it started. The displacement is 0 meters. Average velocity for the first 10 seconds. Again, it's average 10 seconds. At 10 seconds, its displacement here is 8 meters west. So average velocity is displacement, putting a P there, over time. So its displacement is 8 meters west, and it was 10 seconds, so the average velocity is 0.8 meters per second west. So 0.8 meters per second west. What is the average speed? Well, it went 6 meters east, it went 6 meters west, and then it went another 10 west. So 6 plus 6, another 8. 6 plus 6 plus 8 is 20. So the average speed is distance over time. So 20 meters over 10 seconds, the average speed is going to be 2 meters per second. No direction because it's speed. Okay? Hopefully that makes a bit of sense. Don't worry, I have another one of these to give you tomorrow. So there will be more practice, I promise. But for right now, we're going to go and take a look at velocity versus time graphs. So you also have this sheet, okay? Velocity versus time. So what's the slope of a velocity versus time graph? So if you take a look over here, and if you can see over there, I can be very impressed. On this side is velocity, on this side is time. So the y2 minus y1 will be like vf minus vi, and the x2 minus x1 will be like delta t, or tf minus ti, sorry, be consistent, tf minus ti. So this will be delta v over delta t. What is delta v over delta t? It is acceleration. So the slope of a velocity versus time graph is the acceleration. Okay, so we're back on the PowerPoint now for your notes. So the slope will be the acceleration of the object at that particular time or over that time interval. So again, if the slope isn't changing, then the acceleration is the same for the whole thing. The size of the slope, the magnitude of the slope, will tell us how quickly it's changing speed, and the positive or negative will tell us is it speeding up or slowing down in a particular direction. Okay? So, just like before, what is this object doing? Okay, the slope is constant and positive, which means the acceleration is constant and positive, which means the object is speeding up in a positive direction. The second one, the slope is constant but negative. So that means the acceleration is constant but negative. So that means that the object is slowing down, and we can see it's going like 40 or something there down to 0. It's slowing down, but in a positive direction. How do I know it's a positive direction? Because it's above the line, right? It's going from 40 down to 0. So it's slowing down, but it's traveling in a positive direction. If it was traveling in a negative direction, it would have to be below the line here. C, what is C doing? Well, the slope is 0, which means the acceleration is 0. Doesn't mean the object isn't moving. The object is actually moving at a constant velocity, okay, in a positive direction. How do I know? Because, again, it's above the x-axis. It's above the 0. So this object is traveling at a constant velocity in a positive direction. The next one, there are supposed to be two objects here, A and B. So they are both traveling at a constant velocity in a positive direction, but one is traveling faster than the other, right? Because one is at a higher spot on the graph, so one's traveling faster than the other. Next side. Again, you have two objects, A and B. I was aiming to try to get them equally distanced. They're both traveling at constant velocity because both of their slopes are 0, which means they're not accelerating. But one is traveling in the positive direction and the other is traveling in the negative direction. This might be 3 and this might be negative 3. Okay? F. This object starts at a positive speed, slows down, slows down, slows down, stops, and turns around and goes in the other direction. So its acceleration is constant but negative, right? So it's traveling in a positive direction, slowing down, switches direction, and now begins to speed up. So constant acceleration, slowing down in a positive direction, speeding up. This is throwing a ball up in the air, right? Traveling in a positive direction, slows down, stops, travels downward, speeds up. This guy, the acceleration is not constant. The velocity is increasing, getting bigger, getting bigger, getting bigger, but not at a constant rate. All right, couple more. How do we find the velocity at a particular time? Look at the graph. If I want the velocity here at 1 second, I go up, I read it off the graph. It's 8 seconds. What's the average velocity and the average speed? Exactly what it was on the displacement versus time graph. These are the ones that are tricky. Distance, you have to find the area under the graph and then add them up. Displacement, area under the graph, but you have to take directions into account. What do I mean by that? So I'd find this area,